Welcome to Science for Sleep, where wonder and calm meet. Each night we drift through galaxies, oceans, and mysteries of the natural world, not to startle, but to soothe. So, take a deep breath. Let curiosity slow your thoughts, and fall asleep to the sound of discovery. The ocean, beneath the ocean, an invitation into the world of underwater lakes. There is a moment, somewhere in the vast darkness of the deep sea, when the world suddenly seems to fold in on itself. A diver or remotely operated vehicle approaches what looks unmistakably like a shoreline, complete with rippling waves, lapping edges, and a shimmering surface. But this shore doesn't belong on land. It doesn't belong under sunlight or sky. Instead, it exists thousands of feet beneath the ocean's surface, buried in eternal darkness where sunlight can no longer reach. And yet the illusion is so complete that the mind almost refuses to accept what it sees. These are the underwater lakes and rivers of the deep sea. Enigmatic bodies of dense, toxic brine pooled into valleys and trenches like miniature oceans inside the ocean itself. They are among the most surreal and otherworldly environments ever discovered on Earth. Places where physics, chemistry, and biology combine to create scenes that feel more like science fiction than reality. Underwater lakes form in a world governed by crushing pressure, freezing temperatures, and perpetual night. They occupy a realm that seems designed to repel life. And yet life persists here, in forms that challenge everything we think we know about biology. Some creatures slide across the lake beds as if walking along a shoreline. Others hover above the shimmering surface, dipping in and out of the brine as though testing an alien landscape. Even the brine itself behaves strangely, resisting the surrounding seawater, holding onto its shape, and flowing like a river across the ocean floor. The density difference between the brine and the seawater is so great that the two fluids never truly mix, creating visible boundaries, clear waves, and reflective surfaces in a place where such phenomena should not exist. It is a world where the familiar rules of the ocean break down and are replaced with something entirely new. To understand these underwater lakes, one must first imagine the deep sea itself. The journey downward is like leaving Earth behind in slow motion. As sunlight fades, the blues and greens of the upper ocean darken into muted grays, and then, plunge by plunge, dissolve into complete darkness. Suan disappears into a heavy stillness. The pressure increases dramatically, rising by 1 atmosphere every 10 meters. By the time you are 1,000 meters deep, the pressure is enough to crush metal and deform structures not specifically engineered for the depths. And yet, life adapts. From bioluminescent predators to ghostly drifting jellyfish, everything here has evolved to withstand conditions that would instantly kill most surface-dwelling organisms. It is within this almost alien environment that underwater lakes form, silent, hidden, and waiting for discovery. Some of these lakes exist in the Gulf of Mexico, some in the Red Sea, and others scattered across the world's oceanic basins. They appear in forms ranging from tiny pools only a few meters across to sprawling lakes stretching hundreds of meters in length. Known officially as brine pools, they form when salt deposits buried beneath the sea floor dissolve and seep upward, creating super salty water so dense that it sinks and settles into depressions like liquid mercury. The boundaries are sharply defined. A robotic camera can hover just above the lake's surface and clearly see the difference between regular seawater and the shimmering brine. If the craft descends too far, it will hit the surface of the brine and bounce upward, just as if it had landed on a thick, viscous layer. The illusion is uncanny, as if a small robotic submarine has stumbled onto a hidden lake inside the ocean, complete with waves, ripples, and reflective glints from the lights shining upon it. The psychological effect of encountering such a place is profound. Even seasoned oceanographers describe the experience with a sense of awe and disbelief. The human brain is conditioned to associate the concept of a lake with sky, sunlight, shorelines, and open air. Yet here, in total darkness, a lake forms without any of those references. It is a reminder of how easily the natural world can surprise us, how even on Earth, our well-mapped, well-studied planet, there remain places that feel entirely new, as if Earth is presenting glimpses of worlds that could exist on distant planets. What makes these lakes even more enigmatic is their chemical composition. Many brine pools are not simply salty, they are infused with lethal concentrations of methane, hydrogen sulfide, and other toxic compounds. Their dense liquid is deadly to most known marine organisms. A fish, accidentally drifting into the pool, will not swim out. Instead, it will sink and die almost instantly, overwhelmed by the suffocating brine that strips oxygen from its tissues. Yet, paradoxically, the edges of these lakes teem with life. Mussels gather in thick clusters around the brine pool's rim, feeding on chemosynthetic bacteria that use chemical energy instead of sunlight. Tube worms anchor themselves to the nearby sediments, drawing nutrients from unseen microbial partners. Strange amphipods dart just above the lake's surface, never touching the deadly brine, but surviving within millimeters of it. These life forms create vibrant ecosystems perched on the border between two worlds: regular seawater above and a toxic, alien lake below. To a scientist, this juxtaposition is astonishing. To a storyteller, it is mesmerizing. And to a curious mind, it is irresistible. How can life flourish so close to death? Why do such environments exist at all? What forces shape them, maintain them, and populate them with such unusual species? Each underwater lake feels like a self-contained universe, with its own rules, its own chemistry, and its own strange inhabitants. And the more scientists study them, the more they realize that these lakes are not merely ocean oddities. They are windows into the past and future of life on Earth. They may resemble the conditions that existed billions of years ago when primitive life first emerged. They may also offer clues about where life might exist on other planets, on Europa, Enceladus, Titan, and beyond. In this exploration, we will journey into the heart of these underwater lakes. We will trace their origins, examine their deadly chemistry, and meet the creatures that thrive on their margins. We will descend into the darkness where the ocean forms lakes inside itself. Places that defy expectations, challenge our understanding of biology, and reveal the astonishing creativity of nature. As we move through each chapter, the calm, immersive flow of the story will guide you deeper, while the science enriches your understanding of these surreal environments. This is not just an exploration of the deep sea. It is an exploration of boundaries, between water and brine, between life and death, between the familiar and the unknown. In these quiet, the descent into darkness, entering the realm where underwater lakes form, the descent into the deep ocean begins as a journey through gradients of fading light, a slow and graceful slipping away from the familiar world above. The sunlit waters of the epipelagic zone shimmer with life and color. But as you drift downward, the warmth of light diminishes, and the ocean begins to reveal its true depth. At around 200 meters below the surface, the light thins into ghostly blue ribbons, weak and fleeting. It is here that the twilight zone begins, a realm where sunlight struggles to penetrate, where shadows dominate, and where creatures adapt to a life suspended between day and night. The descent is quiet, almost peaceful, as if the ocean is slowly closing the door to the bright world above and inviting you deeper into its secrets. By 1,000 meters, the final traces of sunlight have vanished entirely, This marks the beginning of the midnight zone, a place where darkness is eternal and pressure grows relentlessly. The weight of the ocean bears down with a force that multiplies with every meter descended. Machines built for this journey must withstand pressures of hundreds of atmospheres. Human divers must remain inside specialized submersibles, enclosed in thick titanium spheres that protect them from forces strong enough to collapse steel. In this permanent night, life has evolved in ways unimaginably different from what exists near the surface. Eyes become enormous to capture the faintest glow. Bodies become transparent. Some creatures depend on bioluminescence, tiny bursts of light created within their own bodies, to communicate, lure prey, or confuse predators. As you continue downward, the water temperature drops steadily. By 2,000 meters, it hovers near freezing, but it never becomes solid because the crushing pressure alters the very behavior of water. This realm feels alien, a world sculpted by physics that seems unfriendly to life, yet somehow gives rise to forms that defy expectations. It is within this zone, between roughly 700 and 3,000 meters in depth, that underwater lakes begin to appear. They form in the calm, cold silence, nestled in depressions of the seafloor, pooling in trenches, craters, and fault lines. They do not announce themselves dramatically. There is no sudden boundary or glowing marker that indicates their presence. Instead, they are discovered only when cameras or vehicles drift close enough for their shimmering surfaces to emerge from the darkness like hidden mirrors. The first signs that you have entered the realm of underwater lakes are subtle. The seafloor begins to flatten and then dip into shallow basins. Sediments thicken. Strange chemical signatures appear in the water, hinting at changes invisible to the naked eye. The water becomes slightly cloudier with suspended minerals. And then, like a mirage, a reflective sheet forms ahead. It glints in the submersible's lights, creating the illusion of a horizon where none should exist. The brain protests at first, trying to reconcile the impossibility of a lake beneath the ocean. Yet the illusion persists. The shoreline curves gently. The surface ripples softly under the vibrations of the submersible's thrusters. It is a world within a world, a lake inside the sea. Its existence owed entirely to density, pressure, and the strange chemistry of Earth's crust. These underwater lakes form because of ancient salt deposits buried deep beneath the ocean floor. Millions of years ago, when sea levels dropped and shallow basins dried up, thick layers of salt and minerals settled onto the seabed. Over time, as the oceans returned and tectonic forces pushed and pulled the crust, these salt deposits became trapped beneath layers of sediment. The pressure and heat from the earth below eventually caused the salt to dissolve into highly concentrated brine. Because this brine is far denser than normal seawater, often several times saltier, it seeps through the sediments and gathers into pools rather than diffusing into the ocean around it. The result is a liquid that behaves almost like a separate substance, refusing to mix with the surrounding seawater and forming lakes, rivers, and even small cascading waterfalls, where the dense brine flows over the contours of the seafloor. The descent into these environments is not just a physical journey. It is a journey through gradients that reveal how profoundly different the deep ocean is from the surface world. Above, the ocean is driven by sunlight, wind, and surface currents. Below, everything is shaped by pressure, chemistry, and the slow movement of geological forces. The creatures that live in the deep have evolved to exist on the razor's edge between survival and collapse. Their bodies must resist crushing pressure yet remain flexible. Their metabolism must function in freezing water with limited nutrients. Their sensory systems must compensate for the absence of light. And yet, Even in such an unforgiving environment, life finds ways to thrive. The seafloor at these depths is often surprisingly uneven. It may appear flat in places, but at others it descends into long, narrow trenches carved by tectonic shifts. These depressions serve as natural basins where brine collects. The lakes that form in them can be several meters deep, with clear edges that mimic a shoreline. The surfaces of these lakes are so distinct that robotic submarines can land on them as though landing on ice, bouncing slightly due to the density difference. The submersible's lights illuminate the shimmering surface, revealing a smooth, glass-like texture that resembles quicksilver or oil. When currents sweep across it, the brine forms tiny waves that lap against the lake's boundaries. Waves that move slowly, methodically, as if time itself is heavier down here. The descent also reveals dramatic shifts in the behavior of chemicals and minerals. Hydrogen sulfide becomes more common. Methane bubbles rise from the seafloor, forming pockets that fuel specialized communities of bacteria. These bacteria form the foundation of entire ecosystems that thrive without sunlight. Instead of photosynthesis, life in these regions depends on chemosynthesis, the ability to convert chemical energy into biological energy. It is a process that seems almost magical in a world dominated by darkness, and yet it mirrors the potential for life on other worlds, where sunlight may be scarce or entirely absent. As you approach an underwater lake, the surrounding landscape begins to change. The sediments may take on different colors: reddish hues from iron, pale patches from mineral crusts, darker streaks from organic deposits. The edges of the brine pool often host clusters of mussels or tube worms, forming thriving oases around the toxic lake. The creatures here hover at the boundary, never venturing into the brine itself. They know instinctively that it is deadly. Many brine pools are so toxic that even a slight dip below their surface is fatal to most marine animals. The brine suffocates them by preventing oxygen uptake, and the chemical composition can disrupt their cells almost instantly. The dead bodies of fish and crabs lie at the bottom of some brine pools, preserved in the dense, oxygen-poor liquid, like ancient relics frozen in time. As the submersible draws closer to the lake, the sense of scale becomes overwhelming. You realize that you are drifting over one of the strangest landscapes on Earth, a place few humans have ever witnessed. The pressure outside is immense, but inside the submersible, the environment feels strangely peaceful. The lights illuminate the lake's surface, casting flickers of reflection across the robotic arms and sensors. A sense of calm settles over you, the kind of calm that comes from witnessing something that feels both impossibly rare and deeply serene. The darkness no longer feels threatening. It feels gentle, as if it is cradling the lake in silence. This descent is a reminder that our planet still holds mysteries that rival the landscapes of distant worlds. Scientists studying these underwater lakes often remark that the experience is like visiting another planet without leaving Earth. The combination of deep-sea physics, geology, and biology creates environments so unusual that they challenge our understanding of what life can endure. The journey downward, through layers of diminishing light and increasing pressure, is not merely a passage through depth. It is a passage into an entirely different version of Earth. One where lakes form in darkness, rivers flow underwater, and life thrives at the edge of impossibility. In the quiet, shadowed world where underwater lakes form, the ocean reveals a version of itself that few have the chance to witness. It is a place of profound beauty, danger, and scientific wonder. The descent into darkness is only the beginning of the story. The first step into understanding how such bizarre, mesmerizing environments come to exist. As the journey continues, the mysteries deepen, and the world beneath the waves becomes even more extraordinary. The birth of a brine pool. How an underwater lake comes to life. The creation of an underwater lake begins long before a modern submersible ever drifts above its shimmering surface. It is a story that stretches back millions of years, shaped by ancient oceans, evaporating seas, shifting tectonic plates, and the slow chemistry of minerals transforming beneath layers of sediment. To understand how a lake can exist deep beneath the ocean, one must travel far into the past, to a time when the floor of today's oceans was dry land or shallow water, or trapped behind natural barriers that prevented the free flow of the sea. In those forgotten epochs, salt accumulated in vast beds. Seas rose and fell. Sediments drifted and settled. Over eons, these conditions laid the foundation for the strange phenomenon we now call a brine pool. It begins with the evaporation of seawater in shallow basins. When water evaporates, salt remains behind. In warm, enclosed regions, such as ancient gulfs and inland seas, water once evaporated more quickly than it could be replenished. As the surface receded, it left behind thick layers of crystalline salt. Some of these deposits grew hundreds of meters thick. Over time, new layers of sediment buried the salt, pressing it deeper into the Earth's surface. Geological forces folded and fractured the crust. Some layers of salt became trapped beneath clay, shale, or limestone. Others were twisted into domes, ridges, or pockets, waiting silently beneath the seabed. Salt is a peculiar substance. It dissolves easily, reacts with water readily, and behaves almost like a fluid under immense pressure. As seawater seeped through sediments over millions of years, it encountered buried salt deposits and slowly dissolved them. This process created pockets of brine, extremely salty water far denser than the seawater above. The brine, thick with minerals, could not mix easily with lighter seawater and instead began migrating upward through cracks and fissures. When the brine finally reached the seafloor, it pooled in natural depressions, forming lakes and rivers of salt water so dense that they created clearly defined boundaries within the ocean. The chemistry of these brine pools is astonishing. Some contain nearly 10 times the salinity of regular seawater. Others are infused with sulfides or methane, byproducts of ancient organic matter decomposing deep beneath the sea floor. In the Gulf of Mexico, for instance, ancient salt formations known as Luan salt were buried during the Jurassic period. These massive deposits are now responsible for many of the region's brine pools. As tectonic forces squeezed and fractured the seabed, brine seeped into the ocean basin, where it settled quietly into deep depressions and formed shimmering lakes that look like windows into another world. The density difference between brine and seawater creates the foundation for the lake's surreal appearance. Because the brine is so much heavier, it resists mixing. Even when currents sweep across the seafloor, the brine tends to hold its shape, forming a stable, recognizable surface. This surface can ripple, tilt, and even flow, mimicking the behavior of lakes on land. Some brine pools even have beaches, where the brine meets the surrounding sediment in a sloping curve. The lake's edge is often outlined by a distinctive white crust made of salt and minerals that precipitate out of the dense brine. These mineral borders add to the illusion, making the scene appear even more like an earthly lake. If the formation of brine appears simple on the surface, high salinity leading to high density, the reality is far more complex. Beneath the calm, shimmering pools lies a world of geochemical processes that shape not just the lakes themselves, but the ecosystems that surround them. Many brine pools release methane gas, which seeps upward in bubbles that sometimes burst across the brine's surface. This methane fuels chemosynthetic bacteria, which in turn support mussels, tube worms, and other deep-sea creatures. These ecosystems flourish around the edges of the lakes, drawing energy not from sunlight, but from the chemical breakdown of methane and sulfides. In some regions, the process of brine formation is still ongoing. Fresh brine constantly emerges from below, replenishing the lake and maintaining its density. This upward flow helps the lake retain its distinctive shape. Without this replenishment, mixing with the overlying seawater might eventually weaken the density gradient. But in many cases, the geological system is active enough to maintain the lake for thousands or even millions of years. The brine pool becomes a stable feature on the ocean floor, its chemistry slowly shifting, but its physical form remaining remarkably intact. One of the most fascinating aspects of brine pool formation is how it mirrors processes that could happen on other planets or moons. Subsurface oceans on Europa or Enceladus may mix with minerals beneath the icy crust, creating pockets of brine. If those brines find pathways to the surface, they could form lakes, much like the ones we see on Earth's ocean floor. Even Titan, with its methane and ethane lakes, demonstrates how liquids can pool, resist mixing, and create shoreline-like features in alien environments. Studying underwater lakes here on Earth gives scientists a model for understanding similar phenomena elsewhere, expanding our knowledge beyond the boundaries of our own planet. The birth of an underwater lake is not a single event, but a gradual transformation. Salt dissolving, brine forming, pressure rising, and the dense liquid finding its way upward until it settles into a quiet corner of the ocean floor. Each step in this journey reveals the complex, patient artistry of geological time. Millions of years must pass for the brine to accumulate. Thousands more for it to migrate upward. And once it does, the lake must find a natural depression deep enough to hold it, protected from strong currents that might erode its boundaries. Even after a brine pool forms, it continues to evolve. Minerals precipitate out of the brine, slowly altering the lakebed. Gas seepage changes the chemistry of the water. Microbial communities grow, die, and regenerate. Ripple marks appear across the brine surface as currents pass overhead. The lake becomes a living system, quiet, dark, but utterly dynamic. In some cases, brine pools expand, creeping outward as more brine enters from below. In others, they shrink as geological pressures change or pathways close off. Some even split into two ponds, creating multiple small pools linked by narrow channels of dense brine. The fluid boundaries of these lakes mean that they exist in a state of delicate balance. A strong underwater current or a shift in the sea floor could disrupt the pool, yet most remain remarkably stable, protected by the calm conditions of the deep ocean. Unlike the surface world, where weather, tides, and storms can transform landscapes overnight, the deep sea moves slowly. Time stretches out differently here. Lakes can exist for millennia without significant change. Their surfaces almost perfectly smooth, disturbed only by the occasional movement of a curious creature or the gentle sweep of a submersible's lights. Understanding how these lakes form gives us insight not only into the deep ocean, but into the forces that shape our entire planet. The story of a brine pool is a story about Earth itself. Its shifting crust, its evaporating seas, its buried minerals, and its living ecosystems that adapt to every imaginable condition. It is a story of patience, chemical precision, and profound stillness. And it sets the stage for the extraordinary environments that arise around the lakes, where life thrives at the very edge of habitability. The deadly beauty of brine. Understanding the chemistry of underwater lakes. The moment you encounter an underwater lake, even through the lens of a remotely operated vehicle, you can sense that something is different about the water before you. It shimmers in an almost metallic way, reflecting the submersible's lights with a mirror-like sheen that ordinary seawater cannot produce. The boundary between the brine and the ocean around it is so distinct that the surface appears almost solid, as if you could reach out and touch it. But beyond the beauty lies an invisible chemistry, one that is both deadly and essential to the very existence of these surreal environments. Underwater lakes are chemical worlds unto themselves, their brine thick with minerals, toxic gases, and compounds that make them among the most hostile natural settings anywhere on Earth. To understand the chemistry of these lakes, one must first appreciate their origin. Most brine pools are born from ancient salt beds, but not all brines are created equal. Some are primarily sodium chloride, the same salt that gives seawater its characteristic taste. Others carry a potent mixture of magnesium, calcium, sulfur, and metals. But what truly sets these underwater lakes apart is their staggering salinity. While typical seawater contains about 3.5% salt, brine pools can exceed 20% salt concentration, with some reaching as high as 30% or more. This extreme density is what gives the lakes their structure and prevents them from mixing with normal seawater. At such high concentrations, the brine behaves more like a heavy syrup than water. When a submersible descends too low and touches the brine surface, it does not pass through smoothly. Instead, it bounces slightly, its buoyancy disrupted by the density contrast. Instruments dipped into a brine pool sink slowly, pulled down by the weight of the liquid, but hampered by its thickness. The boundary layer between the brine and seawater forms a shimmering, wavy curtain where light bends and refracts in strange ways. Even sound waves behave differently when they pass through the brine surface, altering how sonar instruments perceive the lake. The chemistry grows even more intriguing and more dangerous when examining the dissolved gases within the brine. Many underwater lakes contain high concentrations of hydrogen sulfide, a gas notorious for its rotten egg smell at the surface, but lethal in high doses. Hydrogen sulfide interferes with cellular respiration, meaning any animal unlucky enough to fall into the lake is essentially suffocated at a molecular level. The brine strips oxygen from tissues faster than the surrounding seawater can replenish it. Fish that accidentally wander into the pool sink lifelessly to the bottom, where their bodies remain preserved in the oxygen-starved environment. Methane is another key component of many brine pools. Released from decomposing organic matter buried deep beneath the sea floor, methane seeps upward through cracks and fractures, sometimes bubbling through the brine in long, shimmering streams. These methane seeps create pockets of energy-rich molecules that fuel specialized bacterial communities. These bacteria, in turn, feed entire ecosystems that thrive near the lake's edge. Without methane, few organisms could survive in these chemical extremes. With it, life not only survives, but flourishes, forming some of the most remarkable ecological networks in the deep sea. Another striking chemical feature of brine pools is the presence of heavy metals. Iron, manganese, copper, and even trace elements like arsenic and lead often collect within the brine. These metals precipitate out of surrounding sediments or rise with the brine from deeper layers. Within the pool, these metals behave differently than in ordinary seawater, forming crusts along the lake's edges or binding with sulfides to create colorful mineral deposits. These deposits lend some underwater lakes a ghostly appearance, with pale white, red, or yellowish rims encircling the brine like the borders of a lunar crater. Yet, for all its toxicity, the chemistry of brine pools is remarkably stable. The density difference between the brine and seawater ensures that the pool remains sharply defined, resisting mixing even when currents sweep overhead. This stability creates a nearly perfect stratification, a calm upper layer of seawater resting atop a dense lower layer of brine. Occasionally, small disturbances ripple across the brine surface, but they rarely penetrate deeply. The brine, heavy and cohesive, behaves almost like a liquid metal, flowing only under specific conditions and retaining its shape unless disrupted by a powerful force. This stratification has profound effects on the physics and chemistry of the surrounding area. Because the brine is so dense, it acts as a trap for organic matter. Dead organisms that fall into the lake remain suspended or sink slowly to the bottom, where they decompose in a chemical soup devoid of oxygen. This decomposition releases even more methane and sulfides, further fueling microbial communities. In some lakes, the bottom layer becomes a thick, gelatinous mud, rich in organic compounds, a kind of deep-sea tar where only the most specialized microbes can operate. The chemistry of underwater lakes is shaped not only by ancient salt beds, but also by microbial activity. Chemosynthetic bacteria do more than feed surrounding ecosystems. They actively transform the lake's chemistry. Some bacteria oxidize methane, others break down hydrogen sulfide, and still others build complex biofilms along the lake's edge. These biofilms can create slippery mats of microbial life that appear like strange, soft carpets draped along the lake's shoreline. Under a submersible's light, they glisten with a texture unlike anything seen in surface ecosystems. One of the most fascinating aspects of these chemical environments is how they mimic early Earth. Billions of years ago, before oxygen filled the atmosphere, Earth's oceans likely contained high levels of methane, sulfides, and other reduced compounds. The chemistry of brine pools may provide a living window into that ancient world, offering clues about how early life could have emerged in similar conditions. Microbes living at the edges of underwater lakes may resemble some of the earliest ancestors of modern life. Organisms that thrived without sunlight and drew energy from the chemical gradients present in their environment. This ancient chemistry has implications far beyond Earth. Scientists studying extraterrestrial environments often look to underwater lakes as analogs for potential alien ecosystems. For example, Europa's subsurface ocean may contain regions where minerals and brine interact in ways similar to Earth's brine pools. Enceladus, with its plumes of chemical-rich water vapor, may host pockets of salty water beneath its icy crust. Even Titan, with its methane and ethane lakes, demonstrates how different liquids can form stable bodies under the right chemical conditions. Studying underwater lakes on Earth helps researchers understand what chemical signatures might indicate life or habitability on other moons and planets. Despite their chemical hostility, brine pools are not static wastelands. They are alive with chemical reaction, microbial reproduction, and slow but steady changes driven by geology. Some pools grow saltier over time as more brine seeps into them. Others may dilute gradually if pathways beneath them close. Still others may split into multiple sections as the landscape shifts. These dynamics turn brine pools into evolving ecosystems, chemically and biologically active despite existing in one of the harshest environments on Earth. The deadly beauty of underwater lakes lies in the balance between stability and danger. Their chemistry supports life but can kill instantly. Their surfaces shimmer peacefully, yet the water beneath can dissolve or suffocate anything that enters. They are places where science and mystery coexist perfectly, where chemical gradients become the foundation for unique ecosystems. Each lake is a chemical landscape, shaped by ancient processes and sustained by ongoing reactions that challenge our understanding of what environments can exist on our planet. Life on the edge. How creatures survive beside deadly underwater lakes. Life in the deep sea is already an act of defiance against extreme conditions, freezing temperatures, crushing pressure, eternal darkness, and scarce nutrients. Yet the organisms that gather around underwater lakes push this defiance even further. They live at the razor-thin boundary between survivable seawater and the lethally dense brine that forms each underwater lake. To exist in this twilight zone, a few centimeters away from certain death, is a testament to evolution's creativity, resilience, and remarkable ability to transform adversity into opportunity. The ecosystems around underwater lakes are not only strange, they redefine the limits of what we consider habitable on Earth. The first thing that becomes apparent when observing life near a brine pool is that the creatures here do not behave like their counterparts in the open ocean. They move cautiously, deliberately, and with an awareness that seems almost instinctive. A fish that strays too close to the brine surface may dip its tail or fin into the dense liquid and immediately struggle, its motions panicked and disoriented. If it slips beneath the surface, it is lost. The brine suffocates it instantly, stripping oxygen from its blood and overwhelming its cells. The fish sinks quickly, drifting to the bottom where its body will remain preserved like a fossil in a chemical tomb. For this reason, most free-swimming animals avoid brine pools entirely, their instincts guiding them away from the shimmering danger below. And yet, surprisingly, the edges of these lakes swarm with life. Mussels, tube worms, amphipods, and other deep-sea creatures gather in dense clusters along the brine pool's shoreline. Their presence here is not a mistake. It is an adaptation. These organisms have evolved to exploit the unique chemical energy available only at this boundary, where methane and hydrogen sulfide seep upward in concentrations high enough to fuel entire ecosystems. In a world without sunlight, chemical energy becomes the currency of life, and the brine pools provide it in abundance. One of the most iconic inhabitants of these regions is the deep-sea mussel. Unlike mussels in surface waters, which rely on filtering plankton, these mussels host chemosynthetic bacteria within their gills. The bacteria convert methane or hydrogen sulfide into nutrients through chemical reactions, essentially performing the deep-sea equivalent of photosynthesis, but using chemicals instead of sunlight. The mussels provide the bacteria with a safe home and access to the steady seep of chemicals. In return, the bacteria feed the mussels from within, forming a symbiotic relationship perfectly suited for life at the edge of a deadly lake. Tube worms, too, are masters of this hostile environment. With no mouths and no digestive systems, they depend entirely on symbiotic bacteria housed within their tissues. The worms anchor themselves in the sediments surrounding the brine pool, extending their feathery plumes into the water to absorb oxygen and chemicals. Their bacteria use these ingredients to create food for the worms, sustaining them in a place where traditional feeding strategies would be impossible. The bright red plumes of some tube worms create a striking contrast against the muted tones of the seafloor, bringing unexpected color to a landscape dominated by darkness. Amphipods, tiny basses, shrimp-like crustaceans, swarm in the waters just above the brine surface. These creatures are exceptionally agile and seem to possess an innate awareness of the boundary below them. They dart quickly, feeding on microbial films, detritus, or organic particles. Their movements are among the most animated in the deep sea, yet they never cross into the brine, as if guided by instinct or evolved sensitivity that warns them of the danger. Their presence is a reminder that the deep sea, despite its reputation for stillness, contains pockets of quick and vibrant life. The microbial communities at the brine pool edge are perhaps the most important life forms in the ecosystem. Invisible to the naked eye, they form the foundation of the entire food web. These microbes thrive on chemical gradients, using energy from methane, sulfides, and other dissolved compounds. Some form biofilms that carpet the lake's edges, creating mats of living cells that glisten under a submersible's lights. Others live within the sediments, forming networks of microbial colonies that process chemicals and stabilize the environment around them. The diversity of microbial life in these regions rivals that of much larger ecosystems, demonstrating how rich and varied life can be even under extreme conditions. What makes this ecosystem even more fascinating is the sharp transition between life and death. The boundary layer, only a few centimeters thick, separates thriving communities from the deadly brine. A mussel anchored just slightly too low may find itself submerged in brine during small shifts in the lake's surface. A tube worm's plume may brush the brine and become chemically burned. Husks of dead animals sometimes line the brine pool's edge, testament to the razor-thin margin between survival and destruction. Yet this same danger fuels life. The chemical seepage that makes the brine deadly also provides the energy that sustains the surrounding ecosystem. Without the toxicity, without the density difference, without the extreme chemistry, the lake would not support any life at all. This paradox, danger giving rise to life, makes underwater lakes some of the most compelling natural laboratories on Earth. Scientists study these areas not only to understand deep-sea biology, but also to explore fundamental questions about life itself. How do organisms adapt to extreme conditions? How do ecosystems form in the absence of sunlight? What strategies allow life to endure at the very threshold of habitability? The answers to these questions extend beyond marine science. They provide insight into the origins of life on Earth and the potential for life on other worlds. For example, in the early Earth, oceans were far more chemically active than they are today. Methane, sulfides, and other reduced compounds were abundant, and sunlight may not have penetrated deeply enough to drive surface-based photosynthesis across the globe. Life may have begun in places remarkably similar to the edges of an underwater lake. Places where chemical gradients provided energy in environments shielded from the harsh surface world. Similarly, the conditions around brine pools resemble potential habitats on Europa or Enceladus, where liquid water, chemical energy, and mineral interactions may create niches for primitive life. Even in the brine itself, despite its toxicity, scientists have discovered microbes capable of surviving short-term exposure. These extremophiles possess molecular tools that help them resist osmotic stress, detoxify harmful compounds, and maintain cellular structure in environments that would destroy most organisms. Their presence suggests that life's boundaries may be even broader than we currently understand. While no complex animal can live within the brine, microbial life may persist as transient visitors, scavengers, or dormant spores. This possibility hints at the resilience of life and the flexibility of biology in adapting to conditions far beyond the norm. The animals living near brine pools do not merely endure these conditions, they depend on them. The chemical richness that gives the brine its deadly nature also creates the energy that sustains the ecosystem. The density difference that forms the lake also creates stability, allowing organisms to establish long-term colonies along its edge. Everything here operates on a delicate balance, a thin line where death sits side by side with survival. The shoreline of a hidden world, ecosystems that thrive at the edge of underwater lakes. The shoreline of an underwater lake is unlike any shoreline on the surface world. There is no sand warmed by sunlight, no vegetation rustling in the wind, no gentle lapping of waves against a beach. Instead, there is darkness, thick, unbroken darkness, and silence weighted by crushing pressure. Yet despite these alien conditions, the edges of brine pools flourish with some of the most complex and surprising life forms in the deep sea. This narrow border, sometimes only a meter wide, is one of the richest habitats in the abyss. Here, chemical energy fuels biological innovation, and evolution expresses itself in ways found nowhere else on Earth. Standing on this shoreline, if one could stand at all, would feel like witnessing a world in delicate balance. Above lies the familiar seawater, home to fish, crustaceans, and drifting particles of marine snow that fall slowly from the upper ocean like faint reminders of the world above. Below lies a dense, toxic brine where no fish can swim, no worm can anchor itself, no creature with gills can survive. And in between, right along the razor's edge, life thrives in vibrant patches, clustering into mats, colonies, and communities that survive only because of the thin transition zone that fuels them. This transition zone is the key to everything. It is here that methane and hydrogen sulfide seep upward through the sediments, meeting oxygen-rich seawater to create powerful chemical gradients. These gradients are the engines of the ecosystem, providing the energy that chemosynthetic bacteria need to convert chemicals into organic matter. Instead of sunlight, these bacteria live on reactions, oxidizing methane or sulfides to build sugars and proteins. In a sense, they are the plants of this underwater world, forming the foundation upon which all other life depends. These bacterial mats spread across the sediments like living carpets. Some are white, others yellow or gray, depending on the minerals and microbes involved. Their texture ranges from smooth and gelatinous to fibrous and rough. As the submersible's lights illuminate the shoreline, the mats glimmer faintly, shifting in appearance with each movement of water or robotic arm. These mats are not passive layers. They are dynamic, responsive communities that expand, contract, regenerate, and adapt as conditions change. They anchor the ecosystem, feeding small grazers, stabilizing the sediment, and converting chemical energy into life-sustaining material. At the edge of the brine, deep-sea mussels form sprawling colonies. Their shells often shine with pearlescent tones or appear coated in sulfur deposits. Anchored in the sediment, they cluster tightly together, sometimes covering entire patches of seafloor like a mosaic of dark shells. Inside each mussel, symbiotic bacteria thrive, consuming methane or sulfides and providing nutrients for their host. The mussels, in turn, provide a structure for other organisms to cling to. Tiny amphipods dart among the shells, and small worms weave themselves between the mussel beds. In some locations, these mussel colonies grow so thick that they form biological reefs, a deep-sea equivalent of coral formations, but built from organisms adapted to chemical rather than solar energy. Tube worms also flourish along this peculiar shoreline. Their long, slender bodies emerge from protective tubes anchored in the sediment. Some species grow only a few centimeters long, while others reach astonishing lengths of up to a meter or more. Their plumes, delicate feather-like structures, extend into the surrounding waterbed to capture oxygen, which their internal bacteria use to process chemical nutrients. These plumes, often bright red or orange due to hemoglobin-like compounds, create a surreal display of color in an otherwise muted habitat. The worms sway lightly in deep-sea currents, forming clusters that resemble underwater gardens. Small predators and scavengers navigate this rich environment with caution. Crabs, drawn to the abundance of mussels and tube worms, patrol the shoreline searching for food. Their movements are slow and deliberate, as if aware of the danger lurking below. A single misstep could send them sliding into the brine. Amphipods scurry across the sediment and bacterial mats, feeding on organic particles without ever descending too far. Some species hover directly above the brine surface, using their agility to stay within millimeters of safety. To the untrained eye, their movements might appear erratic, but these creatures have evolved precise navigation strategies to avoid fatal contact with the lake. Even more curious are the interactions between these creatures. The edge of the brine pool is a bustling neighborhood of small-scale dramas. Predators hunting, grazers feeding, bacteria spreading, worms anchoring themselves, mussels expanding their colonies. Each species depends on the others in subtle ways. The bacteria feed the mussels and worms. The mussels stabilize sediment, allowing bacteria to proliferate. Smaller creatures feed on biofilms and detritus. Predators keep populations in check, preventing any one species from overwhelming the habitat. This balance is delicate, but it creates a surprisingly rich web of life sustained entirely by chemical energy from below. What makes this ecosystem even more remarkable is its stability in the face of constant danger. The brine pool's surface shifts, sometimes rising or falling with slow geological pulses. Small disturbances can alter chemical gradients, forcing organisms to relocate or adapt. Yet life persists, reforming colonies and re-establishing communities as conditions evolve. The creatures here are experts at survival in an environment where safety and death exist only centimeters apart. The shoreline of a brine pool also becomes a resting place, or a final resting place, for many creatures. As fish and crustaceans drift too close and fall into the brine, their bodies settle at the bottom of the lake. Over time, a graveyard forms, silent, preserved, and eerily still. These remains provide nutrients for microbial communities within the brine, but are almost untouched by larger animals, which cannot enter the pool. This creates a unique ecological dynamic where life thrives on the border, but death accumulates below, reinforcing the lake's reputation as both a source of energy and a repository of loss. Despite the harshness of the environment, the shoreline ecosystems surrounding brine pools can remain stable for decades or even centuries. They are insulated from storms, unaffected by seasonal cycles, and protected from surface disturbances by kilometers of water. Yet they are also sensitive to the smallest chemical or geological changes. A shift in methane flow can transform the microbial landscape. An increase in brine seepage can kill colonies that ventured too close. And geological activity can reshape the lake entirely. This paradox of stability and fragility defines life on the edge of underwater lakes. Studying these ecosystems offers insight into the resilience of life and the adaptability of biological systems. The organisms here are not simply surviving. They are thriving in a place that should, by all logic, be uninhabitable. Their existence challenges assumptions about habitability and forces scientists to reconsider the limits of life. In environments of extreme chemistry, pressure, and darkness, life has found a way to flourish in forms as beautiful as they are unexpected. The physics of a hidden shoreline, why brine lakes behave like oceans. Within the ocean, the underwater lakes scattered across the seafloor are astonishing not only for their surreal appearance, but also for their unusual physical behavior. At first glance, they mimic the lakes found on the surface, complete with shimmering surfaces, gentle waves, and defined shorelines. Yet these lakes are not made of ordinary water. They are made of brine so dense and so alien in behavior that they challenge our understanding of how liquids behave under extreme conditions. The physics of an underwater lake is a world unto itself, shaped by density, pressure, salinity, and the unique properties of brine as it interacts with the seawater above it. When you approach an underwater lake, you might expect the brine to simply blend into its surroundings. After all, seawater is a liquid and brine is a liquid. Should they not mix freely? But here, the difference in density is so immense that the two fluids remain separate, forming a sharp and unmistakable boundary. Think of the way oil separates from water. But imagine the separation reversed. Here the brine is the heavier liquid, anchoring itself to the seabed and forming a base layer that the lighter seawater cannot penetrate. This density difference creates something extraordinary: a visible, physical surface underwater. Light refracts differently at the boundary, creating optical distortions. Objects submerged in the brine appear warped or magnified. Ripples move across the surface when currents pass overhead. The brine behaves like a body of water trapped within another body of water, obeying its own rules while interacting with the world above in strange and beautiful ways. The slope of the brine pool's edges adds to the illusion. Just like lakes on land, underwater lakes often have gently sloping banks where the sediment dips down into the pool. These slopes can be coated with mineral crusts, microbial mats, or clusters of mussels adapted to the extreme chemistry. The shoreline forms naturally as brine settles into depressions, filling them from the bottom up. Over time, the boundary becomes stable enough to resist mixing, allowing the lake's form to remain intact for years, decades, or even centuries. One of the most captivating features of underwater lakes is the way they generate small waves. These waves are not as dramatic as those on the surface world. They move slowly and smoothly, but their presence is unmistakable. When a submersible hovers too low, the thrust from its propellers can disturb the brine surface, creating ripples that spread outward in concentric patterns. Underwater currents passing over the lake's surface can also generate subtle undulations. In some cases, methane bubbles rising from below burst through the brine surface, distorting it briefly before the dense liquid calms again. Each disturbance spreads across the surface like a whisper of movement in an otherwise silent world. The physical properties of brine make these waves sluggish compared to those on the surface. Because brine is far more viscous, the energy required to create a wave is higher, and the wave dissipates more slowly. This creates a mesmerizing, dreamlike quality in the movement. A ripple might take several seconds to travel across a small lake. Time stretches in this still world, and even motion seems to occur at a slower pace. This gives underwater lakes their serene appearance, as though time is thicker here, weighed down by the density of the brine. Pressure also plays a critical role in how these lakes behave. At depths of 1,000 to 3,000 meters, the pressure is immense, hundreds of times greater than atmospheric pressure at sea level. This compresses the seawater and the brine differently, altering their respective densities and viscosities. Under these conditions, brine becomes even denser, allowing it to maintain stable boundaries and sharp surfaces. Pressure helps prevent mixing, reinforcing the stratification that defines each lake. Without such extreme pressure, brine pools might behave very differently, losing their structure or diffusing into the surrounding water. But deep beneath the ocean, pressure becomes a stabilizing force, sculpting the lakes into forms that defy intuition. Temperature, too, influences the physics of brine pools. The deep ocean is cold, often just a few degrees above freezing. But the brine pools can sometimes be slightly warmer due to geothermal activity or chemical reactions occurring in the sediments below. These small temperature differences create microcurrents and convection patterns, shaping the behavior of the brine. Warm brine rising from beneath the pool can create gentle upwelling motions, while colder brine settling back into the basin reinforces layers within the lake. These subtle dynamics contribute to the lake's unique structures, creating internal flows that remain invisible to the eye, but detectable through scientific instruments. The shape of the seafloor also influences how brine pools form and behave. Brine brine flows downhill, just like any liquid, and settles in the lowest depressions available. These depressions can be long, narrow channels, creating underwater rivers or circular basins that form true lakes. In some cases, brine flows slowly across the seafloor, following the contours of small valleys and ridges. When it encounters steep slopes, it may cascade downward in slow-motion waterfalls, creating flowing currents within the ocean itself. These brine waterfalls move far more slowly than freshwater falls, but they are no less impressive. They demonstrate how density and gravity interact in the deep sea to create landscapes as complex as any found on the surface. One of the most intriguing physical behaviors of brine is its resistance to intrusion. If an object attempts to enter a brine pool, such as a robotic arm or sampling device, it meets resistance as though pushing into something thicker than water. The brine pushes back, its density acting like a cushion. This makes sampling difficult. Scientists must adjust the buoyancy of their equipment carefully to enter the brine without causing too much disturbance. Even fish that dive too low will bounce off the brine surface before slipping in, an effect that sometimes momentarily saves them, though often only delays the inevitable if they lose control. The brine surface also affects how light moves through the environment. The boundary reflects more light than normal seawater, creating shimmering distortions that resemble heat waves on desert sand. Objects above the surface appear rippled or inverted. A camera pointed downward may capture images that seem surreal. Plants that look elongated, rocks that appear larger, creatures reflected in the boundary as though looking into a shifting mirror. This optical effect contributes to the dreamlike quality of brine pools, making them appear almost mystical as they distort and reshape the light around them. These physics, density, pressure, viscosity, temperature, and optical refraction, work together to create the illusion of lakes, rivers, and waterfalls deep beneath the ocean. They craft a world that challenges intuition, one where the laws of fluid behavior seem to bend into new forms. Yet everything follows predictable scientific rules that reveal the deep ocean as a place where physics manifests in dramatic and unexpected ways. Understanding these physical dynamics not only helps scientists explore brine pools safely, but also helps us appreciate the complexity of the deep sea. The underwater lakes are not passive bodies of liquid. They are active, dynamic environments that interact with the seawater around them, respond to geological forces, and influence entire ecosystems. Their behavior is a reminder that even in a world without sunlight, motion and energy persist through density and chemistry. The evolution of an underwater lake. How brine pools grow, shift, and transform over time. An underwater lake is not a static feature. It is not a frozen pocket of brine locked in place forever. Nor is it an unchanging pool of liquid standing silently in the dark. These lakes are alive in their own way, geologically, chemically, and physically. A brine pool evolves slowly but persistently, shaped by the forces beneath the seafloor and the delicate interactions between brine, seawater, and sediments. Over years, decades, centuries, or even millennia, an underwater lake can grow, shrink, shift its boundaries, or split into new pools. It can become the center of a thriving ecosystem or the site of sudden biological collapse. Understanding this evolution reveals just how dynamic and complex these hidden lakes truly are. The formation of a brine pool begins with the upward movement of dense, salt-rich water from beneath the seafloor. This brine does not appear all at once. Instead, it rises slowly through cracks, pores, and fractures in the sediment. In places where the geological plumbing remains open, brine continues to seep upward continuously, feeding the lakes and allowing them to expand. This fresh influx of brine can increase the lake's depth or widen its boundaries as the dense liquid pushes outward, displacing lighter seawater in the process. The growth is subtle and slow, often changing only a few centimeters per year. But over long spans of time, the transformation can be dramatic. As brine pools expand, they interact with the surrounding sediments. The sediments may shift or collapse slightly under the weight of accumulating brine. In some cases, mineral crystals begin to precipitate along the edges of the lake. These crusts, often composed of halite, gypsum, or other minerals, slowly build up and reinforce the shoreline. The lake becomes bordered by natural walls, sometimes only millimeters thick, sometimes several centimeters, formed from minerals settling out of the saturated brine. These walls create microenvironments where life can anchor itself, and they also help maintain the sharp boundary between brine and seawater. The chemical composition of the brine pool also changes over time. As fresh brine enters, it brings new minerals, gases, and compounds. As organisms die and decompose within or near the brine, organic matter contributes to changes in chemistry. If methane seepage increases, the brine may become richer in hydrocarbons. If sulfide concentrations rise, the lake may take on a stronger toxic character. These chemical shifts influence which organisms can survive at the edges, which bacteria dominate the ecosystem, and how stable the pool remains. Because brine pools are dense and cohesive, they move across the seafloor with slow gravity-driven flow. They follow the contours of the terrain, settling first in low points and then creeping into adjoining depressions as the pool grows. In some locations, the brine may spill gently over a natural ridge, creating a brine waterfall that flows into a neighboring basin. This process can eventually link two depressions, forming networks of connected lakes and streams. The movement is slow but persistent, like thick syrup flowing downhill. The resulting landscapes are intricate and interconnected, resembling river systems or lake chains on land, except formed entirely beneath thousands of meters of seawater. Sometimes, changes beneath the seafloor can cause a brine pool to shrink or fragment. If the geological pathways that supply brine become blocked, the lake may gradually dilute as seawater mixes in from above. The distinct boundary begins to soften. The shimmering surface becomes less defined. And over time, the pool may split into smaller pockets or vanish altogether. When this happens, the ecosystems that depend on the chemical energy from the brine pool begin to collapse. Mussel beds thin out. Tube worms die off. Microbial mats shrink or shift as chemical conditions change. The slow decline can reshape the biological landscape as dramatically as a storm reshapes a shoreline on land. Geological events can also transform underwater lakes rapidly. Submarine landslides, sediment flows, or tectonic tremors may disrupt the seafloor, burying portions of the brine pool or shifting the sediments that contain it. In some cases, brine pools, once thought stable for decades, have changed in mere moments due to geological activity. These rapid transformations demonstrate how dynamic the deep sea can be, how landscapes shift even in the silent darkness of the ocean floor. The evolution of brine pools also affects the organisms that inhabit nearby regions. Mussels and tube worms anchor themselves on stable sediment. But when the lake shifts, they must either adapt to new chemical conditions or perish. Microbial communities migrate with chemical gradients, sometimes forming new colonies as the lake grows or abandoning old ones as chemical conditions decline. Amphipods follow food sources and avoid the lake's encroaching edge. Predators adjust their hunting grounds. Every shift in the brine pool sends ripples through the surrounding ecosystem, creating a constant interplay between geological processes and biological responses. In some rare cases, brine pools expand so significantly that they engulf surrounding terrain, forming massive lakes that dominate entire regions of the seafloor. These megapools can be hundreds of meters wide and several meters deep, forming vast chemical basins unlike anything else in the ocean. The ecosystems around these giant pools are more complex, with multiple biological zones forming around different chemical gradients. The edges are alive with dense communities of mussels and tube worms. While slightly further away, the chemical influence fades, supporting more traditional deep-sea organisms. Closer to the brine, the environment becomes too hostile for anything but specialized microbes. This tiered arrangement of life resembles ecological zones found on land, from lush wetlands to barren deserts, compressed into just a few meters of space. The dynamic nature of brine pools also makes them extraordinary record keepers of geological history. By studying the layers of sediment formed at the pool's edges, scientists can reconstruct ancient changes in methane flow, mineral composition, and biological activity. These layers act like tree rings, documenting periods of growth, decline, and sudden transformation. In some lakes, preserved remains of animals that fell into the brine provide clues to the deep-sea food web stretching back centuries. The chemical signatures of the brine itself reveal shifts in subsurface geology, changes in pressure, temperature, and mineral deposits that occurred long before humans ever set eyes on these hidden lakes. Over time, underwater lakes may even influence larger geological processes. The dissolution of salt beds beneath the ocean can alter the stability of seafloor sediments, contributing to collapses or shifts in the landscape. The chemical reactions occurring within the brine may influence mineral formation. The biological activity around the lake's edge can alter the structure of sediments, as organisms burrow, anchor, and build colonies. While brine pools are small compared to the vastness of the oceans, their long-term geological impact can be surprisingly far-reaching. The evolution of an underwater lake is a reminder that even the darkest, quietest corners of the earth are alive with change. The deep sea is not a static landscape, but a place of constant motion, slow, subtle, patient, but undeniably dynamic. The lakes that appear so still on the seafloor are in fact moving through geological time, shaped by physical and chemical forces that continue working in silence. Rivers and waterfalls beneath the sea, the flowing landscapes of underwater lakes. There is a moment as you drift in a submersible along the seafloor, when the ocean reveals a sight so unexpected that even seasoned explorers pause in stunned silence. Ahead lies not a still pool, but a flowing stream, an underwater river winding across the seafloor as if obeying the rules of a world above. It curves gently, following the contours of the terrain. It has a visible surface, a direction of flow, and in some places, it even has small waves. And in rare instances, the river does more than flow. It falls. The dense brine spills over short ridges and cliffs, creating underwater waterfalls, slow, thick cascades of liquid that drop into deeper basins below. These are not illusions. They are not tricks of light or misinterpretations of current. These are real rivers and waterfalls, formed entirely beneath the ocean's crushing depths. They are the result of dense brine moving across the seabed, guided by gravity, shaped by geology, and the kind of quiet determination that transforms pockets of the deep sea into landscapes as dynamic as anything found on land. To see an underwater river is to witness a collision between two worlds: the familiar physics of liquid movement and the alien environment of the abyss. The existence of brine rivers begins with the simple but profound fact of density differences. Brine, far saltier and denser than seawater, behaves almost like a heavy liquid metal. It flows downhill, seeking the lowest point available, pooling and spreading in ways that mirror the behavior of rivers on land. It does so slowly, sometimes creepingly slow, because of its viscosity and the quiet stillness of the deep sea. Yet over time, the brine carves distinct paths along the ocean floor. These paths become channels, guiding the movement of the dense liquid and shaping the landscape in subtle but measurable ways. Imagine a shallow depression forming a natural valley on the seabed. Brine seeping from the sediments collects in this valley, filling it with dense, shimmering liquid. As more brine emerges, it overflows the valley's edges. Where the terrain dips or slopes downward, the brine moves, forming a continuous stream that hugs the contours of the seafloor. This stream, dense, slow, and mesmerizing, becomes an underwater river. It can stretch for meters or even hundreds of meters, depending on the terrain and the volume of brine. Sometimes it branches, forming tributaries. Sometimes it widens into flat pools before narrowing again into channels. What makes these rivers so captivating is the clarity of their boundaries. The surface of the flowing brine is sharply defined, almost glass-like. When you look closely, you can see the brine sliding beneath the seawater above, glittering in the submersible's lights. The surface ripples slightly, shaped by the motion of the brine itself and by currents passing above. The edges of the riverbanks may be crusted with minerals or lined with microbial mats, creating a distinct shoreline. The river becomes not just a body of dense liquid, but a flowing piece of landscape, alive with movement, yet eerily silent. Underwater waterfalls form when a brine river encounters a sudden drop in the seafloor. The dense liquid spills over the edge, falling slowly but gracefully into a deeper basin below. These waterfalls move at a fraction of the speed of surface waterfalls, their motion dampened by viscosity and pressure. But the effect is still dramatic. The cascade appears as a smooth sheet of shimmering fluid, its surface glinting under the lights. The brine plunges downward, mixing slightly with the surrounding seawater before settling again at the bottom, where it forms a deeper pool. In some locations, such waterfalls are surprisingly large, several meters tall and spanning multiple meters in width. They are thought to be among the largest cascading fluid features on Earth, rivaled only by the waterfall formed by cold, dense water flowing into the deep basins of the Atlantic. Yet these brine falls remain hidden from sight, accessible only to deep-sea probes and manned submersibles. The movement of brine across the sea floor also influences the surrounding sediment. As brine flows, it can erode soft sediments, carving shallow channels. These channels may become deeper over time, creating miniature canyons or gullies. In some regions, brine flow exposes buried layers of minerals, creating colorful streaks along the riverbank. The brine's chemical nature means that sediments can become cemented together, forming hard crusts that define the river's path. This combination of erosion and deposition turns the underwater landscape into a dynamic, evolving terrain. Life responds to these flowing brines in remarkable ways. Microbial mats form along the riverbanks, feeding on the chemical gradients created by the moving fluid. As the brine flows, it carries dissolved methane and sulfides, creating continuous energy sources for bacteria. Mussels and tube worms anchor themselves along the edges, forming colonies that trace the river's shape like vegetation, tracing the banks of a terrestrial stream. Amphipods hover just above the brine surface, feeding on detritus carried in the flowing liquid. Even predators, such as deep-sea crabs, patrol the riverbanks in search of prey, drawn to the chemically rich environment. The river's movement also creates microhabitats. In regions where the flow is slow, sediments may settle gently, allowing microbial mats to grow thicker and more diverse. In faster-flowing regions, the constant movement prevents buildup, creating cleaner, more exposed surfaces. These variations mimic the zonation found in rivers on land: slow pools, swift currents, calm banks, and dynamic channels, all compressed into the narrow confines of the deep sea. One of the most astonishing observations is how these rivers interact with underwater terrain features. Brine has been seen flowing around obstacles, splitting into multiple streams or merging back together downstream. In some rare cases, brine can pool on one side of a ridge until the fluid pressure builds enough to force a breach, sending a sudden surge of brine cascading into a new basin. These events can dramatically reshape local ecosystems, providing new chemical resources to some areas while depriving others. The existence of these flowing brine features raises profound questions about the nature of fluid dynamics under extreme pressure. The deep sea dampens motion, slows turbulence, and suppresses mixing. Yet even here, liquid movement persists, not driven by wind or weather, but by gravity and density. The rivers and waterfalls beneath the sea are reminders that fluid behavior is a universal phenomenon, one that persists even in the most alien of environments. Understanding these flowing landscapes is crucial for scientists attempting to map deep-sea ecosystems. The movement of brine determines where mussel beds grow, where microbial communities thrive, and where chemical gradients are strongest. It influences how nutrients are distributed and how organisms evolve over time. It shapes the physical structure of the seafloor and alters geological processes in subtle but extensive ways. Creatures of the chemical frontier, animals that depend on brine lakes to survive. Life at the edge of an underwater lake does not merely tolerate extreme conditions, it exploits them. In a world where light cannot reach, where the water is near freezing, and where pressure crushes anything not adapted to the depths, organisms have evolved to use the brine pool's chemical richness as a source of energy. They live within centimeters of a deadly boundary, relying on precise instincts and adaptations to survive. These animals form one of the most unusual biological communities on Earth, thriving not because the environment is gentle, but because it is harsh beyond imagination. One of the most iconic inhabitants of this chemical frontier is the deep-sea mussel, a species that has become synonymous with brine pool ecosystems. These mussels do not rely on filtering plankton or organic debris for nourishment. Instead, they form a remarkable partnership with chemosynthetic bacteria living inside their gill tissues. The bacteria use methane or hydrogen sulfide, compounds abundant around brine pools, to generate nutrients. In effect, the mussel becomes a living greenhouse hosting internal plants that convert chemicals into food. This relationship allows mussel beds to flourish in places where ordinary marine life cannot survive, forming sprawling colonies along the edges of brine pools. Their shells often shimmer under the lights of a submersible, coated in mineral films or sediments that reflect the chemical character of the lake beneath them. Tube worms are equally extraordinary. Lacking a mouth, digestive system, or stomach, they depend entirely on symbiotic bacteria housed within their bodies. These worms extend their feather-like plumes into the surrounding water, absorbing oxygen and chemicals that their internal microbes use for chemosynthesis. The worms then feed off the nutrients created by these bacteria. The delicate plumes wave gently in the deep sea currents, creating an almost garden-like appearance in the darkness. For many scientists, the first glimpse of a tube worm cluster at the edge of a brine pool evokes the image of alien flora, thriving in conditions no terrestrial plant could withstand. Close to the brine pool, organisms must be even more careful. A slight dip too low, a movement in the wrong direction, and the brine will consume them. Yet amphipods, small, shrimp-like crustaceans, seem to dance along the boundary with astonishing grace. They hover just above the shimmering surface, never touching the deadly liquid, but using the chemical-rich environment to feed on bacterial mats and detritus. Their agility is perhaps their most important adaptation. In the slow-motion world of the deep sea, where movements are measured and deliberate, amphipods move with surprising speed, darting in quick bursts as they forage among mussel shells and worm clusters. Crabs are frequent visitors to brine pool edges. Their sturdy bodies allow them to patrol the shoreline in search of food, often scavenging dead fish or feeding on smaller organisms that gather around the rich chemical environment. But even these thick-shelled creatures must be cautious. Many deep-sea crabs have been observed approaching the brine pool carefully, stopping abruptly when the chemical signature of the brine registers in their sensory systems. A misstep can be fatal. If a crab slips into the brine, it will die almost instantly, and its body will sink to the bottom of the lake, preserved for years in the oxygen-poor environment. Perhaps the most biologically fascinating creatures at the brine pools are the microbial communities that underpin everything. These microbes perform the essential chemosynthetic reactions that support the ecosystem. Some consume methane, others oxidize hydrogen sulfide, and still others specialize in breaking down complex organic compounds within the brine. Together, they form a living chemical factory. They coat rocks, sediments, and even the shells of mussels in thin, shimmering films. These microbial mats can be smooth and glossy or thick and textured, depending on the species present and the chemical conditions of the environment. The diversity of these microbes is staggering. In some brine pools, scientists have identified hundreds of microbial species living within inches of each other, each adapted to a slightly different chemical niche. Some microbes thrive in hypersaline conditions. Others prefer the border, where chemicals mix with seawater. Some live inside the tissues of animals, while others cling to sediments or drift freely through the water. Each species contributes to the complex chemical and biological processes that sustain the brine pool ecosystem. The boundary between the seawater and the brine is especially rich in microbial life, because it is here that chemical gradients are strongest. Microbes rely on these gradients like plants rely on sunlight. The sharp transition from oxygen-rich seawater above to oxygen-depleted brine below creates layers within which different microbes specialize. Some feed on chemicals rising from the brine, others consume oxygen from the seawater, and still others position themselves in the precise location where both elements are available in balance. The result is a layered tapestry of microbial activity, each layer playing a unique role in the ecosystem. Many larger animals depend indirectly on this microbial abundance. The mussels and tube worms rely on internal microbes for survival. Amphipods feed on microbial biofilms. Crabs scavenge animals that died after venturing too close to the brine pool. Even fish, though they avoid the brine itself, may hunt the creatures drawn to the lake edge. This creates a food web unlike any found in sunlit environments. A system fueled not by plant life or photosynthesis, but by pure chemistry and microbial ingenuity. The adaptations of these creatures are not limited to feeding strategies. They extend to their physical bodies. Many brine pool organisms have evolved specialized proteins and cellular structures that protect them from chemical exposure. Some mussels possess gills capable of processing high sulfide concentrations. Tube worms have protective tubes that shield them from sudden increases in toxicity. Microbes have evolved enzymes that detoxify harmful compounds. Every organism, from the smallest bacterium to the largest crab, has been shaped by the demands of life beside a deadly lake. The ecological relationships around brine pools also reveal a delicate balance between life and death. The lake is a source of energy, but also a constant threat. A brine pool may offer a steady supply of chemicals, but it also presents risks from fluctuating boundaries, shifting sediments, or sudden increases in toxicity. Animals at the lake edge must adapt to tiny changes in the environment, changes that may be imperceptible to human sensors, but critical to survival. This chemical frontier highlights evolution's ability to produce life in places that seem utterly inhospitable. It demonstrates that ecosystems do not require sunlight or warm temperatures to flourish. They require only energy from any source, and organisms capable of using it. In the darkness of the deep sea, where chemical energy becomes the currency of life, underwater lakes create pockets of abundance in a desert of cold and pressure. The graveyard. Beneath the waves, death, preservation, and the silent depths of brine pools. The edges of underwater lakes are places of thriving life, but just a few centimeters deeper, beneath the shimmering surface of dense brine, lies a world where life cannot endure. The brine itself is a chemical trap, lethal, oxygen-stripping, suffocating, and corrosive to living tissues. Any creature that accidentally crosses the boundary, whether by a slip, a fall, or a moment's disorientation, is lost. And because the brine contains so little oxygen, the animals that die within it do not decay as they would in the upper ocean. Instead, they settle gently onto the lake bed, preserved in near-perfect form. Over time, a silent graveyard accumulates at the bottom of the brine pool, creating a haunting record of life and death in one of the most extreme environments on Earth. If you peer into a deep brine pool through a submersible window, you may see the pale shapes of fish lying motionless on the lake bed. Their bodies are intact, their fins still extended as if frozen in time. Crabs, too, lie scattered across the basin floor, their shells unbroken, their limbs preserved. The effect is eerie and surreal. It is as if the lake has collected ghostly remains and arranged them in a still tableau, victims of a boundary that offers no second chances. This preservation happens because the brine actively prevents decomposition. Decomposition in marine environments requires oxygen, a variety of microbes, and a water chemistry that allows biological and chemical breakdown. But within a brine pool, oxygen is virtually absent. The oxygen-rich seawater above forms a sharp and impenetrable boundary, and oxygen cannot diffuse into the brine in meaningful amounts because of its extreme density and chemical composition. Without oxygen, many of the microbes responsible for decay cannot survive. As a result, decomposition slows dramatically or stops altogether. Hydrogen sulfide within the brine also contributes to the preservation. This compound is toxic to most organisms, killing not only the animals that fall in, but also many of the microbes that would normally feed on their remains. What microbial activity does occur is slow and specialized, often producing only partial breakdown over long periods. Methane in the brine adds another layer of chemical complexity, altering the environment in ways that further inhibit decay. The result is an environment where the dead remain suspended in time, resting on the lake bed in quiet, unchanging stillness. This preserved graveyard tells a story about the brine pools themselves. Each skeleton or intact body is evidence of the pool's power. Creatures that misjudged the boundary or were pushed by currents, predators, or chance. Some fish appear to have chased prey too close. Others seem to have drifted down slowly, perhaps weakened or disoriented. Crabs, with their exploring claws and cautious steps, sometimes miscalculate and slip over the edge. The brine does not discriminate. Once an animal enters, the dense liquid closes around it, and escape becomes impossible. For scientists, These graveyards offer unique opportunities to study deep-sea life. The preserved remains can reveal details about the species that inhabit the surrounding area, their sizes, their feeding habits, and even how they interact with the brine pool environment. Some scientists compare these lake beds to natural museums, display cases of creatures that lived near the chemical frontier, each one preserved by a combination of chemistry and pressure. But these graveyards also raise questions about the behavior of deep-sea creatures. Why do animals approach the brine pools at all? The answer reflects both instinct and necessity. Brine pools are sources of chemical energy, and life around them is abundant. Predators are drawn by the presence of prey. Scavengers follow the scent of organic material. Free-swimming animals may sense food distributions or temperature gradients that lead them close to the edge. In the deep sea, resources are scarce, and animals must explore every opportunity for nourishment. Even a deadly lake can attract life, and sometimes the margin between survival and death becomes too thin to navigate. In some brine pools, the accumulation of dead animals is so pronounced that the lake bed resembles a layer of bones. Entire patches may be covered in fish skeletons or crab carapaces, preserved in chilling stillness. Among them, microbial mats may form, feeding off the slow chemical release from decomposing tissues. This creates a secondary food web within the brine itself, a web sustained by death. The irony is profound. In a place where life cannot survive, life still finds a way to feed and grow on the remains of those that succumbed. The presence of graveyards also highlights the contrast between danger and abundance in the brine pool ecosystem. The edges support some of the richest communities in the deep sea. Yet a few centimeters deeper lies a deadly trap. This juxtaposition creates a tension that defines life at the brine pool. Every creature must be aware of the boundary. Every movement must be measured. Some species have evolved heightened chemical sensitivity, able to detect the brine even in minute amounts. Others rely on learned behavior or instinctive avoidance. Yet despite these adaptations, accidents happen and the graveyards grow. Mysteriously, some brine pools seem to contain only certain species in their depths. In one region, fish remains dominate. In another, crabs are more common. This suggests that different species interact with the brine pools in different ways. Some may be more prone to chemical confusion, others more likely to venture close in search of food. Understanding these patterns is an ongoing scientific effort, requiring careful observation and advanced sensing equipment to track animal behavior around the pools. It is also possible that, for some animals, the brine pools act as natural traps. The shimmering boundary can distort vision in unexpected ways. Light refracting through the brine surface can create illusions of depth or movement. A fish chasing prey might misinterpret a reflection as another fish or mistake the brine surface for open water. In the slow-motion world of the deep sea, where sensing is difficult and light is scarce, even a small optical mistake can be fatal. There is a haunting beauty to these graveyards. It is a beauty born not from tragedy alone, but from the stillness and clarity that the brine imparts. In the deep sea, where currents constantly shift sediments and bodies decay rapidly, such pristine preservation is rare. Brine pools offer a glimpse into a frozen moment, an underwater mausoleum where life and death meet at the boundary of a silent, shimmering lake. These preserved remains also help researchers understand how long brine pools persist. The age of the trapped remains, their condition, and the chemical layers around them can provide clues about the pool's stability, growth, and geological history. In some cases, layers of remains suggest that the pool has existed for centuries, accumulating victims slowly over time. In others, the graveyard may be sparse, suggesting a younger or more dynamic pool. A window into ancient Earth. What underwater lakes reveal about our planet's early oceans. The underwater lakes scattered across the deep sea are not just strange modern phenomena. They are time machines. Hidden beneath kilometers of water, brine pools preserve chemical conditions reminiscent of Earth's distant past. Conditions that existed billions of years before the first complex life evolved, when the planet was young, volatile, and filled with oceans far different from those we know today. These surreal lakes offer scientists an unparalleled glimpse into what early Earth might have looked like, how ancient oceans behaved, and how life could have begun in environments that were chemically rich but sunless, toxic, and extreme. To understand why underwater lakes serve as windows into ancient Earth, one must step back into deep time, back to an era when Earth was a molten world gradually cooling, when volcanic activity shaped the landscape, and when the atmosphere contained little to no oxygen. During this period, the oceans were a chemical cauldron, filled with dissolved metals, methane, sulfides, and countless compounds created by hydrothermal activity. Sunlight may have penetrated only shallow depths, and even there, early life had to contend with ultraviolet radiation, fluctuating temperatures, and unstable conditions. The deep ocean, however, offered something different: stability. Even in the planet's infancy, the deep sea would have been dark, cold, and shielded from the chaos above. Chemical reactions fueled by mineral-rich water from the seafloor could have provided a constant and reliable source of energy. In this sense, the deep sea environments we see today, especially those around brine pools, are not merely strange anomalies, but echoes of ancient habitats where life might have first taken root. The chemistry of brine pools closely resembles the chemistry of early Earth's oceans. The pools are rich in hydrogen sulfide, methane, and various metal ions, exactly the kinds of compounds believed to have been abundant in the planet's primordial waters. These chemicals are toxic to most modern organisms, but they provide the raw materials for chemosynthesis, a process that predates photosynthesis in evolutionary history. Chemosynthetic microbes living around brine pools use chemical gradients to create organic molecules from inorganic compounds, much like early life forms would have done billions of years ago. Examining these microbial communities reveals features that seem ancient. Many of the bacteria found at brine pool edges share characteristics with some of the earliest known microbial lineages. They thrive in low-oxygen environments, tolerate extreme salinity, and use chemical reactions that mirror those of early Earth's microbes. Their metabolic pathways, ways of extracting energy, resemble biochemical strategies believed to have existed long before photosynthesis emerged as a dominant energy source. This connection has profound implications for our understanding of life's origins. If early organisms evolved in environments similar to brine pools, then the first ecosystems may have been built around chemical energy rather than sunlight. Life may have begun not in shallow, sunlit waters, but in dark, mineral-rich depths where chemical gradients provided a steady and abundant source of energy. This idea challenges older assumptions that the first life emerged near the surface, shifting the origin story to a world much more similar to the ecosystems observed around underwater lakes today. Brine pools also demonstrate how stable chemical environments can foster complex biological communities. Despite their toxicity, brine pools maintain consistent conditions over long periods, allowing microbial communities to adapt and diversify. In early Earth's chaotic environment, stability would have been rare and precious. Deep sea basins filled with chemically rich water may have offered sanctuaries where life could establish itself without being constantly disrupted by storms, temperature fluctuations, or ultraviolet radiation. The layered structure of brine pools is another clue to ancient Earth. Each pool contains distinct chemical zones: oxygenated water above, anoxic brine below, and a thin boundary layer where the two interact. These gradients create different habitats within just a few centimeters of space. Early Earth's oceans likely featured similar gradients, not from brine, but from volcanic gases, hydrothermal activity, and sediment interactions. Studying how microbes organize themselves along these gradients today provides insights into how early life may have structured itself in ancient waters. The mineral deposits around underwater lakes also resemble geological features from Earth's early history. As brine interacts with seawater, minerals precipitate out, forming crusts, nodules, and layers rich in metals and sulfides. These mineral structures are similar to ancient formations found in the geological record, evidence that chemical reactions between seawater and mineral-rich fluids were common in Earth's past. Some researchers believe that the earliest fossil-like structures, including stromatolites, may have formed in environments not unlike the modern brine pool edges. Furthermore, the interactions between brine, microbes, and minerals create self-sustaining cycles that could have fueled early biological evolution. Microbes alter the chemical environment through their metabolic activity. This, in turn, changes the minerals that form, which then affect the availability of nutrients and energy. These feedback loops represent the kind of interplay that could have shaped early ecosystems. They also illustrate how life and geology intertwine, a relationship that continues to define Earth's biosphere even today. The study of underwater lakes also extends beyond Earth, offering insights into where life might exist elsewhere in the universe. If Earth's early oceans resembled environments near brine pools, then similar conditions could support life on other planets or moons. Europa's subsurface ocean, for instance, may contain chemically rich pockets created by interactions with its rocky mantle. Enceladus, with its geysers of mineral-laden water vapor, may host brine-rich reservoirs beneath its icy crust. Titan's lakes of methane and ethane demonstrate that liquids can form stable bodies even in the coldest regions of the solar system. By examining brine pools here on Earth, scientists can better understand the possibilities for life in alien oceans. The microbes that thrive in these lakes demonstrate that life can adapt to extreme salinity, chemical toxicity, high pressure, and complete darkness, conditions that might be common in extraterrestrial environments. The systems created around brine pools show that ecosystems do not need sunlight or organic-rich water to flourish. Instead, they need chemical energy and a stable environment, two factors that may exist beneath the icy surfaces of distant moons. Brine pools are more than geological oddities. They are time capsules that preserve the ancient chemistry of Earth's earliest oceans, laboratories where evolution's oldest strategies still operate, and guides that point toward the types of environments where life might emerge on other worlds. The more we learn about these underwater lakes, the more we uncover about the dawn of life on Earth and the potential for life elsewhere in the cosmos. As we continue our journey, the next chapter will take us into the geological forces that shape these lakes. How tectonic activity, buried salt layers, and ancient seas sculpt the strange landscapes we now explore deep beneath the waves. Sculpted by the Earth, the geological forces that shape underwater lakes. The underwater lakes, resting quietly in the deep ocean, did not appear by chance. Their existence is the result of immense geological processes that unfold over millions of years. Forces powerful enough to shape continents, yet subtle enough to carve tiny basins on the seafloor. Brine pools are, in many ways, the geological fingerprints of Earth's restless interior. They form where tectonics, ancient seas, sediment layers, and the steady rise of buried minerals intersect. Understanding these forces reveals how dynamic the Earth truly is, even in places where darkness and silence seem eternal. The geological story of an underwater lake begins long before the ocean itself takes its present shape. Millions of years ago, during prehistoric eras when sea levels fluctuated dramatically, vast inland seas evaporated under scorching climates. These ancient waters left behind enormous salt deposits, thick layers of halite, gypsum, and other evaporite minerals. Over time, these deposits became buried beneath accumulating sediment. As the weight of the sediments increased, the salt compacted, shifted, and in some places began to flow like a slow-moving plastic material. Buried salt behaves differently from most rocks. It moves under pressure, forming dome-like shapes known as salt diapirs. These diapirs rise through overlying layers like bubbles rising through batter, warping the seafloor above them. As tectonic plates shift and continents drift, these buried salt bodies become squeezed, fractured, and dissolved. When seawater infiltrates cracks in the sediment, it encounters the buried salt and begins dissolving it. The dissolved salts produce dense, mineral-rich brine that accumulates in underground pockets. Over time, the pressure inside these pockets increases. Eventually, a pathway opens, perhaps through a fracture created by tectonic stress or through a pore channel widened by chemical reactions. When this happens, the brine slowly rises toward the sea floor. This upward migration is often slow and persistent. Brine seeps through sediments for centuries, millennia, or even millions of years. When it finally reaches the seafloor, it emerges as a dense plume that sinks immediately into any nearby depression. This creates the earliest form of a brine pool. The depression might be a crater formed by ancient geological activity, a slump in the sediment caused by salt movement, or the remnants of a collapsed salt dome. Whatever its origin, the basin becomes the home of the newly formed underwater lake. But the story doesn't end there. Once the brine pool forms on the seafloor, it begins to interact with the geological environment around it. Sometimes the brine collects in deep pits. In other cases, it spreads across gently sloping terrain. The pool may widen as more brine seeps upward or form tributaries that extend into nearby depressions. This creates dynamic landscapes where brine flows like a slow-moving glacier, guided entirely by gravity and the shape of the seafloor. Tectonic activity continues to play a role even after the lake is established. Small earthquakes, shifts in sediment, or deep-sea landslides can alter the shape of the lake basin. These events may break open new pathways for brine, causing the pool to expand. Or they may block existing pathways, slowly starving the lake of new brine and causing it to shrink. Over geological time, entire brine pools may migrate across the seafloor, following shifting depressions or responding to the rise and fall of salt layers deep below. To a human observer, the lake appears still and eternal. But on geological timescales, it is constantly in motion, like a heartbeat hidden under the Earth's crust. Another key geological force shaping underwater lakes is the interaction between hydrothermal activity and salt layers. In some regions, heat from beneath the crust warms pockets of brine, making them more buoyant and encouraging their upward movement. This geothermal influence can produce brine that is not only salty, but warm, unusual for the deep sea, where temperatures are near freezing. When this warm brine meets cold seawater, it creates distinct layers and chemical gradients that contribute to the formation of mineral crusts around the lake's edge. Salt tectonics, the movement of salt layers under pressure, is another powerful factor. Salt domes can rise hundreds of meters, pushing sediment upward and creating complex seafloor topographies. These domes may crack, allowing brine to escape. They may collapse, creating deep pits into which brine flows. They may even create ridges and channels that guide the movement of brine rivers. In the Gulf of Mexico, many underwater lakes owe their shape and position to ancient salt domes that formed nearly 170 million years ago. As brine pools interact with geological forces, they leave behind evidence of their evolution. Mineral crusts form along the edges of the lake, creating hardened borders that resemble ancient shorelines. Layers of mineral-rich sediment accumulate at the bottom of the pool, recording chemical changes over time. Microbial mats grow on mineral surfaces, creating biological markers of past geochemical conditions. Each layer, each crust, deposit, and shift becomes part of the geological archive, documenting the lake's history in silent detail. In some regions, the brine itself influences geological development. The dissolution of salt layers beneath the seafloor can lead to instability, causing collapses or sediment shifts. If brine flows repeatedly through certain pathways, it can carve channels or create vents. These vents may eventually become the source of new brine pools or feed existing ones. The interplay between brine and geology is continuous. Brine shapes the seafloor, and the seafloor shapes the brine. These geological processes also help scientists understand how brine pools on other worlds might form. On Europa, for example, salt water beneath the icy crust could behave like the brine beneath Earth's seafloor, moving upward through cracks, pooling in pockets, and forming under ice lakes. On Enceladus, hydrothermal activity at the ocean floor may produce chemical gradients similar to those found around brine pools. Even on ancient Mars, evidence suggests that salt-rich basins and subsurface brines once existed. The geological stories of underwater lakes on Earth may therefore mirror the geological histories of distant worlds, hinting at environments where alien life might one day be discovered. The deep sea may seem static and unchanging, but every underwater lake is proof that Earth is alive with motion. Tectonic forces shift the crust beneath our feet. Salt beds dissolve and transform. Brine rises, flows, and settles. Basins form, collapse, and reshape themselves. Over millions of years, these forces create landscapes of startling complexity. Lakes beneath the ocean, rivers of dense brine, and mineral-crusted shorelines hidden in permanent night. As we continue our journey, the next chapter will explore the remarkable role of hydrothermal systems, methane seeps, and energy-rich chemicals. How these invisible forces feed life, alter chemistry, and shape the brine pools into the thriving ecosystems we see today. The hidden engines, methane seeps, hydrothermal activity, and the energy that fuels underwater lakes. Deep beneath the ocean's surface, far from the sunlight that nourishes most life on Earth, energy still flows, quietly, invisibly, and relentlessly. This energy is not born from light, but from the planet itself. It seeps upward from the crust, carried by chemical-rich fluids, methane bubbles, hydrothermal activity, and ancient salts dissolving beneath kilometers of sediment. These hidden engines are the driving forces behind underwater lakes. Without them, the brine would not form. The chemical gradients would not exist, and the ecosystems surrounding these lakes would have no energy source to sustain life. Methane seeps are among the most influential of these engines. Methane, a simple molecule composed of carbon and hydrogen, is produced deep within the Earth by both geological and biological processes. When organic matter becomes buried in the sediment, whether ancient plant remains, algae, or marine creatures, microbial decomposition produces methane as a byproduct. Meanwhile, geological processes within the Earth's crust generate methane through chemical reactions involving heat and pressure. Over millions of years, these methane reservoirs become trapped beneath layers of rock and sediment. Eventually, the gas begins to migrate upward, finding pathways through cracks and fissures created by tectonic forces. When methane reaches the sea floor, It escapes into the surrounding water as shimmering bubbles that rise slowly in the deep sea stillness. In regions where brine pools form, the methane gets trapped within the dense brine, dissolving into the liquid and adding to its chemical richness. The presence of methane is crucial because it fuels chemosynthetic bacteria, microorganisms that form the very foundation of brine pool ecosystems. These bacteria consume methane, converting it into organic matter through complex biochemical pathways. This process, known as methane oxidation, is one of the earliest known metabolic strategies on Earth, dating back to a time when sunlight was scarce and the young planet was rich in volcanic gases. Hydrogen sulfide, another product of subsurface activity, plays an equally important role. Produced through microbial sulfate reduction or geological reactions involving sulfur minerals, hydrogen sulfide seeps into brine pools alongside methane. This gas is toxic to most animals, but is a vital energy source for sulfide-oxidizing bacteria. These microbes use hydrogen sulfide in chemical reactions that generate energy, allowing them to grow, reproduce, and form the thick biofilms that coat the lake's shoreline. These microbial mats, in turn, provide food and habitat for other organisms, creating a complex web of life rooted entirely in chemical energy. Hydrothermal activity also contributes significantly to the formation and sustainability of underwater lakes. In some regions, heat from magma beneath the Earth's crust warms pockets of groundwater. This heated water dissolves minerals from the surrounding rock, becoming enriched with chemicals like iron, manganese, and sulfur. As this mineral-laden water rises through the crust, it may mix with buried salt layers, producing even more concentrated brine. When the warm mineral-rich fluid reaches the seafloor, it encounters the cold ocean water and cools rapidly, depositing minerals and contributing to the chemical diversity of the brine pool environment. Some brine pools are located near hydrothermal vents, where black smokers and white smokers pour out superheated mineral-rich fluids. Although brine pools are typically formed through different processes, the proximity of hydrothermal vents enhances the chemical complexity of the region. The minerals from vent systems settle in sediments, interact with brine chemistry, and create habitats rich in metals and sulfides, elements that support diverse microbial life. This interplay between hydrothermal systems and brine pools demonstrates how interconnected deep-sea ecosystems can be, with one geological process influencing another in subtle but profound ways. These hidden engines also shape the physical structure of the brine pools. Methane bubbles rising through sediments can create small craters or pits as they disturb the seafloor. Over time, these pits can become depressions where brine accumulates. Meanwhile, the dissolution of salts by warm, mineral-rich fluids can create sinkholes or basins that serve as natural reservoirs for brine. Some brine pools form directly above areas of high methane flux, where gas continuously rises from deep subsurface reservoirs. The constant influx of methane-rich brine helps maintain the pool's density and stability, ensuring that the lake remains a long-lasting feature. The interplay between methane seeps and brine pools has another fascinating consequence: the creation of carbonate structures. When methane is consumed by bacteria beneath the seafloor, one of the byproducts is bicarbonate, which can combine with calcium or other minerals to form carbonate rocks. These rocks can build up along the edges of brine pools, creating hard, reef-like formations. Over time, these carbonate structures become habitats for additional organisms, adding complexity to the landscape. They also serve as markers of past methane activity, preserving evidence of chemical reactions that occurred centuries or even millennia ago. The chemical energy flowing through these environments supports intricate food webs. Methane-eating microbes sustain muscles that house bacteria within their gills. Sulfide-eating bacteria support tube worms that rely entirely on their internal microbes for nourishment. Amphipods feed on microbial films or organic particles produced by chemical reactions. Crabs and other scavengers take advantage of the dense animal populations supported by chemosynthetic communities. All of this is made possible by the hidden engines beneath the seafloor. Methane seeps, sulfur fluxes, hydrothermal circulation, and the slow dissolution of ancient salt beds. Despite their complexity, these engines operate quietly and persistently. Methane seepage continues for centuries, sometimes even hundreds of thousands of years. Hydrothermal systems pulse with energy over geological timescales. Salt layers dissolve gradually, providing a steady supply of brine. These processes are not fleeting events. They are long-term geological mechanisms that shape entire ecosystems. Understanding these hidden engines also provides insight into other parts of the planet, and even into possible life on other worlds. On icy moons like Europa or Enceladus, chemical gradients between water and rock could drive similar energy cycles. Hydrothermal vents beneath ice-covered oceans may release minerals and chemicals, much like those that feed brine pool ecosystems on Earth. If life exists there, it may rely on chemosynthesis, just as brine pool organisms do here. These similarities make brine pools valuable analogs for studying extraterrestrial environments where sunlight cannot reach, but chemical energy thrives. Masters of extremes, evolutionary adaptations that allow life to thrive around underwater lakes. Life at the edges of underwater lakes is not merely unusual, it's astonishing. These animals and microbes navigate an environment where danger lies only centimeters away, where chemistry is poisonous, pressures are crushing, temperatures hover near freezing, and light is forever absent. Yet somehow, in this forbidding place, life flourishes. The secret lies in the extraordinary adaptations that evolution has crafted over millions of years. Innovations that allow organisms not just to survive these conditions, but to depend on them. Studying these adaptations reveals how far the boundaries of life can stretch, and how deeply evolution can sculpt biology when faced with extreme environmental pressures. One of the most striking adaptations found around brine pools is the symbiosis between animals and chemosynthetic bacteria. Mussels, tube worms, snails, and certain shrimp species do not rely on traditional feeding methods. Instead of mouths and digestive systems that process food particles, many host bacteria within their tissues. These bacterial partners convert methane or hydrogen sulfide, chemicals abundant around brine pools, into organic molecules that nourish their hosts. This mutualistic relationship is so efficient that some animals have completely lost their digestive systems. They have traded the complexity of feeding for the stability of chemical energy. Tube worms, perhaps the best-known inhabitants of such environments, display this adaptation vividly. Lacking mouths, stomachs, or intestines, they possess an organ called the trophosome, which houses millions of chemosynthetic bacteria. Their feather-like plumes contain specialized hemoglobin capable of binding both oxygen and hydrogen sulfide, a rare biochemical feat, as sulfide is normally toxic. This allows tube worms to deliver the raw chemical ingredients their bacterial partners need while simultaneously transporting oxygen for respiration. The plumes wave gently in the deep sea currents, maximizing exposure to the thin boundary layer between oxygen-rich seawater and sulfide-rich brine, a delicate balancing act perfected over millions of years. Deep-sea mussels rely on similar adaptations. They house methane-oxidizing bacteria within their gills, providing them with a constant supply of nutrients even in the absence of particulate food. Their shells often grow thicker and more robust than those of shallow water mussels, helping them withstand the crushing pressures of the deep sea. Some species even exhibit specialized tissues that allow them to regulate internal chemistry as sulfide or methane concentrations fluctuate. This biochemical flexibility is crucial, as the chemical environment around brine pools can change rapidly depending on seep activity and brine movement. Crabs and amphipods, though not directly dependent on chemosynthesis, exhibit adaptations that help them navigate the perilous surroundings. Many possess advanced chemoreceptors, specialized sensory structures that allow them to detect minute changes in the chemical composition of seawater. This helps them sense the boundary of the brine pool without touching it. Some amphipods demonstrate remarkable agility, darting away instantly when their antennae detect even small increases in salinity. Crabs, although slower, have learned to patrol only certain parts of the shoreline, avoiding direct contact with the brine except when absolutely necessary. Fish, despite their vulnerability to the brine, have been observed lingering near brine pool edges, likely sensing prey or organic particles drifting from the rich ecosystem around them. These fish often possess heightened pressure tolerance and specialized swim bladders that allow them to hover at precise depths without sinking into danger. Their lateral line systems, the organs responsible for detecting vibrations and changes in water movement, may also help them avoid the dense brine boundary by sensing the subtle currents created as the brine and seawater interface. But some of the most remarkable adaptations are found at the microscopic level. Microbes that inhabit these environments have evolved complex biochemical pathways that allow them to detoxify sulfide, tolerate hypersaline conditions, and survive in complete darkness. Many possess enzymes capable of functioning at high pressures and low temperatures, conditions that would disable or destroy the proteins of most surface organisms. Some microbes have thickened cell membranes rich in special lipids that maintain fluidity in extreme salinity. Others have genetic repair mechanisms that protect them from chemical damage caused by sulfide exposure. One particularly fascinating microbial adaptation is the formation of biofilms, sticky, structured mats composed of millions of cells working together. These biofilms form protective layers that allow microbes to stabilize their environment and shield themselves from chemical fluctuations. Within the biofilm, different microbial species may occupy specific layers, each tailored to a particular chemical niche. The upper layers may contain bacteria that process oxygen and methane, while deeper layers house those that thrive on sulfide or other reduced compounds. This vertical structuring resembles a miniature ecosystem, with organisms arranged according to their metabolic needs. Some microbes engage in syntrophic relationships, cooperative partnerships in which the metabolic byproducts of one species fuel the growth of another. These interactions are essential in environments where chemicals are abundant, but usable energy is scarce. For example, one microbe may convert methane into a compound that another microbe can metabolize more efficiently. Together, they create a stable biochemical network that supports the broader ecosystem. Even more unexpectedly, some bacteria around brine pools possess genes similar to those found in extremophiles from hydrothermal vents, hypersaline lakes, and even icy environments. This suggests that extreme adaptive traits have been shared and reshaped over long stretches of evolutionary time. The deep sea becomes a melting pot of survival strategies, where life borrows, modifies, and reinvents tools to endure in harsh conditions. Larger organisms also exhibit adaptations that go beyond biology and enter the realm of behavior. Mussel beds and tube worm colonies often form in patterns that maximize their collective access to chemical gradients. Mussels may cluster in dense, overlapping shells that create sheltered microhabitats for smaller creatures. Tube worms may orient themselves in particular directions to take advantage of gentle currents that bring fresh chemicals into the ecosystem. These behaviors are not random. They are shaped by evolution to optimize energy intake and minimize exposure to danger. Some species have adapted to exploit the vulnerability of others. Predatory fish may linger above the boundary of a brine pool, waiting for amphipods or small crustaceans to venture too far from safety. Crabs may scavenge animals that died after slipping into the brine. Even these predators must be cautious, however, for a single mistake can turn hunter into victim. The extreme environment also shapes reproductive strategies. Many deep-sea organisms produce larvae that drift through the ocean before settling near a suitable chemical environment. These larvae must detect specific cues, chemical signatures that indicate the presence of methane seepage or sulfide-rich sediments. Only by choosing the right habitat can they survive to adulthood. This dispersed reproductive strategy helps maintain genetic diversity and ensures that populations can recover from disturbances such as brine pool shifts or collapses. The adaptations found around underwater lakes underscore one of evolution's greatest truths. Life will find a way, even in the most hostile places. Whether through symbiotic partnerships, biochemical innovation, sensory specialization, or behavioral precision, the creatures of the brine pool have mastered an environment that appears utterly inhospitable. Their presence invites us to reconsider our assumptions about where life can exist and what forms it might take in the universe. In the next chapter, we will explore how scientists study these extraordinary organisms and environments, diving into the technology, methods, and challenges of exploring places where human senses and tools are pushed to their limits. Into the abyss, how scientists explore and study underwater lakes. Exploring an underwater lake is unlike studying any other environment on Earth. Scientists must descend into the deepest parts of the ocean, places where sunlight cannot penetrate, where water pressure is hundreds of times greater than at the surface, and where temperatures hover just above freezing. In these depths, every movement is slow, every observation important, and every piece of technology must function flawlessly. The deep sea is unforgiving, but it is also one of the last frontiers of scientific exploration, and underwater lakes are among its most captivating mysteries. Understanding how researchers reach these hidden worlds reveals the extraordinary lengths we go to in order to unravel the secrets of the planet. The journey begins long before a submersible touches the water. Scientists first use sonar mapping, specifically multi-beam echo sounders, to scan vast stretches of seafloor, looking for depressions, unusual patterns in sediment, or signals that might indicate brine. Because brine pools reflect sound waves differently from ordinary seawater, they appear as distinct anomalies in sonar data. The mapping process can take days or weeks, as large sections of the seabed must be surveyed to locate these hidden lakes. Once a potential site is identified, a remotely operated vehicle, ROV, or Autonomous Underwater Vehicle, AUV, is deployed for closer inspection. ROVs are among the most important tools for studying deep-sea environments. They are tethered to a ship by long cables that transmit power, commands, and high-definition video signals. These machines carry robotic arms, sampling tools, cameras, chemical sensors, and sometimes even small storage chambers for biological specimens. Piloted by experts on the research vessel, ROVs can maneuver delicately across the seabed, hovering just above fragile ecosystems without disturbing them. When approaching an underwater lake, ROV pilots must exercise extreme caution. A sudden dip of a thruster or misjudgment of distance could plunge the machine into the brine, potentially damaging equipment or contaminating the site. AUVs, on the other hand, are free-swimming robots programmed to navigate the deep ocean autonomously. They are used to collect data over large areas, mapping the seafloor, measuring temperature, salinity, and chemical gradients, and identifying potential sites for further study. While AUVs cannot interact physically with the environment like ROVs, they provide crucial broad-scale data that helps scientists understand the geological context of brine pools. For missions that require a human presence, manned submersibles, such as Alvin or the Deep-Sea Challenger, allow scientists to descend directly into the abyss. Inside the small, spherical pressure hull, scientists observe brine pools with their own eyes, watching the shimmering surfaces and the life that thrives along the edges. The experience is profoundly different from watching a screen. Observers describe a sense of vastness and stillness that cannot be conveyed through video alone. In these submersibles, scientists can make real-time judgments, adjust observation plans on the fly, and capture details that remote cameras might miss. Sampling brine from these lakes is a delicate process. Because brine is so dense, traditional water samplers, Niskin bottles for example, must be modified to handle the thick, syrup-like liquid. The sampling device must penetrate the brine without introducing seawater contamination. Robotic arms carefully lower syringes or specialized chambers into the brine, drawing samples that are later analyzed in onboard laboratories. These samples contain information about salinity, mineral content, methane concentration, microbial communities, and the chemical gradients that define the lake's boundary. Studying the life around brine pools requires equally careful methods. Biological specimens, mussels, worms, amphipods, microbial mats must be collected using gentle tools that prevent damage. Some ROVs carry suction samplers that draw organisms into soft collection chambers. Others use small scoops or claws designed to pick up sediment or entire clusters of animals. Once on the surface, these specimens must be handled quickly and kept under controlled conditions. Many deep-sea organisms die rapidly when brought to low pressure, so researchers work to preserve tissues, extract DNA, or maintain the microbial environment long enough to study metabolic activity. Chemical sensors attached to ROVs allow scientists to measure methane, sulfide, oxygen, temperature, and salinity directly above the brine pool. These sensors provide real-time data about the gradients that sustain microbial life. Optical instruments measure how light refracts and scatters at the brine boundary, helping to quantify the physical properties of the lake. Acoustic sensors reveal how sound travels through the brine, offering additional clues about density and structure. In some cases, ROVs also collect sediment cores using slender tubes pushed into the lake bed. These cores preserve layers of sediment and minerals that document the lake's evolutionary history. Microbial research requires the most advanced tools of all. Samples collected from brine pools are often stored in anaerobic containers to preserve their chemical integrity. Once back in laboratories on land, scientists use genomic sequencing to analyze microbial DNA, identifying species and reconstructing metabolic pathways. Metagenomics, the study of genetic material extracted directly from environmental samples, allows researchers to explore entire microbial communities without needing to culture individual species. This technique has revolutionized the study of deep-sea environments, revealing a level of biodiversity that was previously unimaginable. Increasingly, scientists also deploy long-term monitoring equipment around brine pools. These instruments remain on the seafloor for months or years, recording changes in temperature, chemical concentration, and biological activity. They offer insight into the dynamic nature of underwater lakes, how they grow, shrink, shift, and influence surrounding ecosystems over time. Autonomous sensors can detect sudden methane releases, seismic activity, or rapid changes in brine volume. Together, these data streams paint a picture of a living geological system shaped by forces far beneath the surface. Exploring underwater lakes is not without challenges. The equipment is expensive, fragile, and difficult to deploy. Weather conditions at the surface can delay or disrupt missions. Navigation is difficult in the pitch-black depths, where even the most advanced sensors must compensate for limited visibility. And the sheer remoteness of these environments means that every hour of exploration must be carefully planned. Yet despite these challenges, the allure of these lakes, their mystery, their scientific importance, their otherworldly beauty, continues to draw researchers back again and again. Every mission uncovers something unexpected: a new species, a previously unknown chemical process, a geological formation unlike anything seen before. Underwater lakes challenge our assumptions about the limitations of life, the behavior of fluids, and the geological activity of our planet. They remind us how little we truly know about the deep sea and how much there is still left to discover. Underwater lakes also remind us that the natural world is not static. It evolves, shifts, and transforms over time. The lakes themselves grow, shrink, migrate, or disappear, shaped by forces deep beneath the crust. Life adapts to these changes, developing new traits or abandoning old habitats. The deep sea is not a quiet, unchanging abyss. It is a dynamic, living system. The resilience of these environments encourages us to view our own challenges, personal, societal, or global, through a similar lens. Change is inevitable, but with adaptation comes strength. In many ways, underwater lakes symbolize the balance between danger and opportunity. Their boundaries are deadly, yet they sustain rich ecosystems. Their chemistry is toxic, yet life depends on it. Their environment is extreme, yet it fosters stability for those adapted to it. This duality is reflected in many aspects of life. Growth often happens at the edge of comfort. Innovation emerges from adversity. Understanding comes from confronting the unknown. Finally, these lakes teach humility. For all our technologies, our satellites, our scientific instruments, we remain unable to fully grasp the complexity of even a single underwater lake. Each one holds layers of mystery that challenge our assumptions and expand our understanding. This humility is essential. It grounds us. It reminds us that exploration is a continuous journey, not a destination. And so, this journey concludes, not with an ending, but with a reminder. The world is vast. Mystery lives everywhere. And beneath the ocean's deepest layers lie lakes that glow like mirrors, reflecting not only the geology of Earth, but the imagination of those who dare to explore it.